Hello, today I am going to discuss about the Hamming code. Hamming code, obviously is one of the different types of codes that you will study. So here the method of coding is not about just programming a C or C++ language. Here the coding pertains to the coding of message when it is transmitted over a channel. So here let us consider a transmitter and a receiver. This transmitter wants to send a message 1101 to the receiver. Now you can think about what are the advantages and disadvantages of directly sending a message over the channel. First of all, if you send this message directly in this form, then any interceptor in between the channel would be able to look at your message and you will not be able to know about it. And the second thing is, when you send this message, there could be some noise in the channel that might change 1 or 2 bits within this message. Then also at the receiver, let's say instead of receiving 1101, you received 1100, and the receiver doesn't have any mechanism to know that error has occurred in the message. So obviously what we turn to is we use various coding schemes to perform the coding at the transmitter, and appropriate decoding mechanism is employed at the receiver. Now, so what is Hamming code? Hamming code is actually for correcting errors up to 1 bit automatically in the received code. So that means, any code, let's say for example 1101 is converted to a corresponding Hamming code, and instead of sending the message, the Hamming code is sent over the channel, and as it is received, the receiver has a decoding mechanism, a proper decoding mechanism to understand the exact location of an error if it all occurred. Okay. Now, so here let us consider our message in general format. Let's say bits N1, N2, N3 and N4. So first of all, this message is clearly is very accurately, it is wrapped up, it is packaged by adding some extra bits to this message. Let's say we are adding 3 extra bits and in this format. That means P1, P2 and P3. Let P1, P2, P3 are the extra bits that we are adding to the message. P1, and we are adding in this format so that P1, P2, N1, then P3, N2, N3 and N4. Okay. So now what is the total length of the message? Let's say if your message length is small n and the number of extra bits that you added is k, then the total length of the message will be n plus k. Therefore L is equal to n plus k. Let us write here. L is equal to total length of the message after encoding, total length of the, or we can say the Hamming code. Okay, Hamming code is L is equal to n plus k. Now this in this format, this code is actually sent over the channel, and after it is received, certain parity checks are performed. Some checks are performed on the received Hamming code to verify whether the received code has any errors or not. So here, our Hamming code, it is able to detect the exact location of any 1 bit error that occurred in this message. So if we assign the locations to our Hamming code, to all the bits in the Hamming code, there will be 1, 2, 3, 4, 5, 6 and 7. Okay. So we have totally 7 conditions, 7 places where the error could occur, and our Hamming code must be able to precisely locate if at all there is an error in any of the 7 places, and also one extra possibility that there is no error, in which case it should be able to detect. So totally we need to have 8 possibilities. Let's say we perform this check C1, C2 and C3 checkings on our received Hamming code. These are the checks, and the location of error. So we need totally 8 possibilities: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, and the location of this error is 0th location, in which case, because there is nothing like a 0th location in our Hamming code, this pertains to the no error condition. Now similarly, 0, 0, 1 correspond to that the first bit received has an error, and the location 2 has an error, 3 has an error, or 4th has an error, 5th has an error, 6th and the 7th have an errors. Now here we can derive one thing, that is, in this case, if error occurs, see, in this case we can observe one thing: C3 is equal to 1 in locations 1, 3, 5 and 7. So we can write like this: if an error occurs in locations 1, 3, 5 and 7, then the C3 bit must be set to 1. Now similarly, if an error occurs in locations 2, 3, 6 and 7, 2, 3, 6 and 7, then C2 is equal to 1. Similarly, if an error occurs in locations anywhere at 4, 5, 6 and 7, then C1 must be set is equal to 1. Okay. So this is a parity checking. Now let us take an example. Let us say take an example. Let us consider that the message that we want to send over the transmission line is 1101. Now this message need to be clearly packed with some 3 bits of information to encode it into a Hamming code, and the locations that we have to do must be in the locations. These some parity bits, some extra parity bits are added to this message, to construct the Hamming code. Let's say P1, P2 and P3 are the parity bits, are the extra bits that we want to add to this message. Then they have to be inserted, P1 in location 2, P2 in location 2, in location 1, P1 in location 1, P2 in location 2, P3 in location 4, P4 in location 8, so on till Pk in location 2 power k minus 1. So these are the locations of our parity bits, locations of parity bits in the message, in the code, in the Hamming code. Now look at this. So P1, P2, then N1, P3, then N2, N3 and N4 in this order. Now we know the values of N1. N1 is equal to, okay, this is our Hamming code. So here N1 is equal to 1, N2 is equal to 1, N3 is equal to 0 and N4 is equal to 1. Okay, but still we do not know the values of these 3 bits that need to be inserted into this message. So we go through what is called as an encoding process, where we make sure that that according to these checkings, that is locations 1, 3, 5, 7, in these locations the bits in these locations must return an even parity. So what is meant by even parity? Even parity is defined as if the number of ones within the message is equal to an even number, then it is said to be even parity. If the number of ones within the message is said to be odd, then it is called as odd parity. So here the P1, P2 and P3 must be selected in such a fashion that these sets of groups will return an even parity. That means in locations 1, 3, 5, 7, that is bits in locations 1, 3, 5, 7. Let us write a table like this. So we have 1, 2, 3, 4, 5, 6, 7 places, and the parity bits are in locations. So our message is in locations 1, 3, 5, 6 and 7. 3 is 1, 5 is 1, 6 and 7 is 0, 1. So now we have to select our parity bits such that these groupings 1, 3, 5 and 7 must return an even parity. Now if you see the locations 1, 3, 5, 7, it corresponds to P1, and the location 3 bit to number 1, 5 is bit number 1, 7th bit is number 1. So if you count the number of ones in this grouping, we have 3 bits here, 3 ones here. So now to make this number an even parity, our P1 must be equal to 1. Implies P1 must be equal to 1, must be set to 1. Similarly, for the locations P2, locations 2, 3, 6 and 7, 2, 3, 6 and 7. Here also we have location 3 is equal to 1, 6 is equal to 1 and bit 7 is equal to 1. Now we have 3 ones here. To now make this an even parity, our P2 must be equal to 1. Now simply this is the encoding process that we should follow. 2, 3, 6 and 7 must return an even parity. Therefore our P2 must be set equal to 1. Similarly, to make 4, 5, 6, 7 even parity, 4, 5, 6, 7 must be even parity, implies our P3 bit. Now look at here, P3 is here, P3 is here in the 4th location, then 1, 6th bit is 0 and 7th bit is 1. Now we have already 1 and 1, 1, 0, 1, which is even parity. Therefore, to keep this even parity as it is, then our P3 must be set to 0. Therefore, we have this following values of the parity bits, that is P1 must be equal to 1, P2 should be equal to 1 and P3 must be equal to 0. Then our complete Hamming code, and the Hamming code is P1 is equal to 1, P2 is equal to 1, then N1 is equal to 1, P3 is equal to 0, then 1, 0, 1 is the Hamming code that need to be sent over the channel. This is the code that is sent to the receiver. Now let us say the receiver, instead of receiving this message, he has received some other message. Let's say, so this is exercise 2. So instead of, so let's say the receiver received, and the receiver received this following message, that is 1, 1, 1, 0, 1, 0, 1. Let's say this is equal to 1. Okay, that is, there is a change in 1 bit from 0 to 1. Okay, so this is a place of the error, location of error. And now let us see if our Hamming code, if this code is able to automatically detect the location of this error. Okay, so how do we do that? So take for example now the X message. Now, so we have to perform the parity checks. Perform 3 parity checks. Now we have these groupings 1, 3, 5 and 7. So if you write down the locations of these bits 1, 3, 2, 3, 4, 5, 6 and 7. 1, 3, 5, 7 bits are 1, 3 is 1, 5 bit is 1, 7th bit is 1. So we already have even parity. So in this case, since the encoding is in even parity and there is even parity in the received bits, then C3 must be set to 0. There is no change in C3. C3 is equal to 0. Now similarly, the grouping 2, 3 and 2, 3, 6 and 7 must be taken. So the second parity check is on 2, 3, 6 and 7 bits. So this will be 2 is 1, 3 is 1, then 6 is 0 and 7 is 1. Here the encoding was in even parity, but the received code is in odd parity. Therefore, some error occurred. Then set this C2 bit is equal to 1. Similarly, check the third condition, that is the bits 4, 5, 6, 7 must return even parity. 4, 5, 6, 7 bits are 1, 1, 0 and 1. Now again we have odd parity. Therefore, the bit C1 is set to 1. Hence, the location of this error is 1, 1, 1, 1, 0 location. Is C1, C2 and C3. The location of error is 6th bit down. Not able to detect.